So we still need to work with and finish up our cell respiration. So far we've gone through glycolysis, and depending on your book, really that's not part of cell respiration, cellular respiration. That's just glycolysis. All cells do that one. They go from glucose to pyruvic acid. They make 4 ATPs. Of course, they don't get to keep all 4 of them because they will do this process again. So they'll use 2 of the 4. So they really get a net gain of 2 ATPs. They do make 2 NADH2s, and so they use those. And then they also make 2 pyruvic acid molecules, also called pyruvate. And those would be the products for that cell respiration, for glycolysis. And then we did talk about ethanol fermentation. So a good many of the bacteria do that, and then also the yeast do that, which we demonstrated in lab. And then some cells do what is called lactic acid fermentation. There are some bacteria that do that. They use lactose sugar, and they do produce a lactic acid through that process. Our cells will do that as well if we have an oxygen debt. So if we run out of oxygen, so that would be like it's going to happen most often in muscle when you're exercising very strenuously. You're working outside in the flower bed and planting and digging holes, and it's very hard to dig holes in West Texas because you go down 3 inches and it's rock. It is just rock. So I like to do lots of planting in Alpine, Texas, and it is also very rocky. So very rarely do I get to use a shovel. It's just a pick. Me and a pick. A pick and me. But I get it done. All right. And so, yeah, I get into a oxygen debt in the muscles, and I do a little bit of lactic acid fermentation, which burns the muscle a little bit. It's not as toxic as a pyruvic acid, which will kill the cell. Lactic acid will just damage it. But once I've rested quite a bit and reestablished my oxygen debt, then lactic acid is converted back into pyruvic acid, and then we do cellular respiration, which begins really with the preparatory reaction, and then you go through the Krebs cycle, also called citric acid, which we did. And the citric acid cycle, well, let's back up. Preparatory reaction, you're going to produce 1 NADH2 for each pyruvate. Of course, you have 2 pyruvates, so that's really, you do that with each one. So you make 2 NADH2s. You also make 1 carbon dioxide there. You release 1 CO2 with each pyruvate. But since you have 2 pyruvates at the end of glycolysis, that you really release 2 carbon dioxides. And then you go into the Krebs cycle, and during the Krebs cycle, you start with a 2-carbon acetyl-CoA, combine it with a 4-carbon, and that gives you a 6, which is called citric acid. And then you release a carbon as CO2, that gives you a 5-carbon molecule. You release another CO2, which you go from a 5-carbon to a 4-carbon, which is called oxaloacetate or oxaloacetic acid, whichever. And then you're back to where you started. So you can bring in another pyruvic acid and run that whole process again. Also during the Krebs cycle, we did make 3 NADH2s. That was for each pyruvate, and we made 1 FADH2. So we're throwing a whole bunch of hydrogens on carriers, and then we did make 1 ATP during that process. Okay, so I just ran through every one of those briefly, all those things that we've looked at. And then now, really, the last thing we need to do is electron transport. So let's first gather all of our hydrogens and our ATPs. So let's look at, say, glycolysis first. Glycolysis, we made a total of 2 NADH2s. So there's some hydrogens that we have collected, NADH2s, collected some there. We also got a net of 2 net ATPs we did make some ATP there. And then if we go directly into if we go directly into cellular respiration, then we go to the preparatory reaction. And I'm going to go ahead and just say this is for both pyruvates. So I'm going to just add numbers as if we run one pyruvate through the prep reaction, then we run the second pyruvate through the prep reaction. So we would actually manufacture two NADH2s right there. And I'll just go ahead and say, well, we've got the two CO2s that come out, one for each pyruvate. And same thing with NAD. You make one of those for each pyruvate. But I'm doubling that. Okay, and then we did the Krebs cycle, also known as citric acid cycle. And so I'm going to do this for both pyruvates. I'm going to go ahead and just add it up. So for each pyruvate, we had generated 2 carbon dioxides for each pyruvate, but we've got 2 pyruvates, so that means a total of 4 molecules of carbon dioxide total. And for each pyruvate, we made 3 NADH2s. So let's say both pyruvates, you're going to make, instead of 3, you'll make 6 NADH2s. And for each pyruvate, we make 1 FADH2. You can go back and look. We made 1 for each pyruvate. So for both pyruvates, that would give us 2 FADH2s. We want those hydrogens. And then for each pyruvate, we made 1 ATP. And so then for both pyruvates, that would give us a total of 2 ATPs. All right. So we're just gathering up everything that we've manufactured. Okay, now all of these hydrogens we want to use, because that's where we really produce most of our energy is from hydrogen. So we're going to gather all of those up. Recognize that these 2 hydrogens are actually in the cytoplasm, those 2 right there. Glycolysis occurs in the cytoplasm, or cytosol. So that's where those are located. All right. So we're going to have to spend some ATP in order to get those into the mitochondrion, because all of these are going to go into the mitochondrion, which we actually have 2 membranes. So we have the outer envelope, which is what you're looking at, and then you have the inner envelope, which is actually folded quite a bit. I don't remember folding it much, but it is folded, something like that. And the folds of this are called the cristae, and I'm sure that is Latin meaning folds. I've never bothered to look that up, but I would throw some money at that if anybody wanted to bet me. And I love to bet. That's probably wrong. It's just another addiction of mine. Just stack it on top of the others. Just throw that one in there. It's one more addiction. What's another one? Yes, ma'am. Well, okay, I didn't list some products. Like, for example, glycolysis, we made 2 pyruvates, right? I didn't list that. But yes, other than that, I'd say yes. Those are the products, things we're making. You could throw 2 pyruvates under glycolysis. I think you'd have a pretty good product list. I just really wanted to show you where you got all your hydrogens. And then while I was doing that, I thought, well, we'll throw the CO2s in there also. Might as well. And the ATPs. Now we've added the pyruvates, so I think we're pretty well covered. We've got it all in there. Okay, so what we want to do is we want to take all of these hydrogens that we put on carriers, NADH2s, and of course in Krebs you did make some FADH2s. They're just hydrogen carriers, that's it. And a good many of those, particularly the 6 NADH2s and the 2 FADH2s, those are already in the mitochondrion. This is where Krebs happens right here. So those are already in here. We don't have to carry them in. These basically are in there as well because that reaction happens right in through here. That's where the prep reaction. So this is where we're doing that prep reaction. So those two are already in there. So the only two that we actually need to carry in are the two that are out in the cytosol of the cell. And so, of course, we are in a cell. So if we need a plasma membrane to help us remember that we're talking about a cell, we'll throw one in. This is the cell. And that's with the mitochondrion in there. Okay, so glycolysis is out in the cytosol of the cell. Prep reaction, I've drawn where that occurs. Krebs cycle, I've just indicated where all that occurs. All right. So the only two NADH2s that we need to carry in are right here. And that takes a little bit of energy to do it. So this really takes 2 ATPs to do that. So if we start adding up all ATPs, we're going to have to subtract 2 because it takes 2 to carry those in. But there will be it is very beneficial to get those in there. Okay, so what we're going to do at this point is we're going to do a process which is called electron transport. And there are molecules that are embedded on the cristae, actually within the cristae. And what we do at those is we pass electrons from one to the next, to the next, to the next. Now, it's a lot more complicated than what I've given you. In fact, all of this is a lot more complicated. But when you get into the next class, they'll go over the same thing, except they'll give you a little bit more information. And then you get into another class, they'll give you the same thing, plus they'll give you even a little bit more information. And then when it's all said and done, you pretty much know every enzyme and where every phosphate attaches at a molecule and when it detaches and where on a molecule you're going to remove the hydrogens and so forth. So we're not at a graduate level yet, so I know you think you're in graduate school, but it sort of feels like it because we're moving that quickly. However, we're not there yet. It is a lot of fun. Some people think graduate school is just going to be horribly difficult. I want to clear that up. In fact, somebody was talking to me about it. I think Monica was talking about that. It's like really hard. No, graduate school is so much fun. In undergraduate work, so like you get a bachelor's degree, you have to take government and history and calculus and all your math stuff and all your English classes, English 1, 2, 3, 4. You're not taking things that you're just specifically interested in, unless those are things you're really specifically interested in, and you're taking the other stuff. But when you get into graduate school, you don't take those things. You're just taking a specific field, and those are things you're interested in. Like I was taking just biology classes, different aspects of biology. Well, I loved that. It was like, man, that was cool. That was fun. I get to know more about those things that I find interesting, and I didn't have to do any calculus or whatever, which I didn't particularly enjoy. Chemistry, PChem 1 and 2, organic chemistry 1 and 2. Could you just shoot me, please, and we'll be past that? Yeah, we'll be past taking all of those things, which were not fun. Anyway, so yeah, graduate school's super, absolutely super. And you're with people who also enjoy that kind of thing. So you get to know people that are more like you than the rest of the world. Because most people aren't like biology people. You have to admit biology people are a little different. We have a different perspective on the world than I think most people would have. We view things differently. So I think really much differently than probably, like English people. What? They're watching your verb, and your, whether you put the right verb in there and the right noun and the past participle and the whatever. You know, your sentence formation. Like, really? You're paying attention to that? That just really must be very boring for you. Although I try very, very hard to speak really good English. And I think it's important to do that. I do. I think it's very, very critical to move forward in life. You know, it depends on how far you want to go. If you want to dig ditches the rest of your life, well, no. You don't need to be able to do that. But if you want to run with the people that you probably would want to run with, then you need to be able to speak to those people correctly, because they will be, and you don't want to look like an idiot. So it helps. All right. Anyway, I got away from all this. I love to get away from all this and just chat a little bit. I think that I call those little mini vacations. I really do. And I think mini vacations. Don't do that. Anyway, they did. All right. So here we are, back at the board. At least I got a good board. I love this. This is good. I have to use markers and things, or chalkboards. God, when's the last time you saw a chalkboard? You know, man. Did you ever see a chalkboard? Any of you? Really? Oh, okay. Well, for what? For talking? No, that's good. I'm glad they still had some. I don't know. Were they black or were they the green ones? Okay, but I mean a blackboard, a real blackboard. Those were cool, very cool. Anyway, um, now they have the paint that you can paint, you know, and then this is what this is. Anyway, okay. So what we're going to do with all these hydrogens, we're going to carry them through. Now, of course, hopefully, hydrogen is nothing but two particles. You have one proton and you have one electron. You understand, hopefully, how this is the end story. The climax of the whole respiratory process is we're going to take and we're going to put all the electrons on one side of a membrane, and we're going to put all the protons on the other side of a membrane, and then at some point we're going to pull the electrons back together with the protons. So the positive charge protons are going to get back together with the negative charge electrons, and that's going to collision of positive and negative. That's the end of the story. So one thing we haven't mentioned is that you really get 3 ATPs for each NADH2 that goes into the electron transport system. 3 ATPs for each NADH2 that goes into the electron transport system. And then you only get 2 ATPs for each FADH2 that goes into the electron transport system. That way we can get some totals on this. How many ATPs are we really making in cell respiration? Well, again, if we're talking about just cell respiration, you have to begin right here. You don't include glycolysis. Really. And that's why the numbers vary. I think your book said, well, there's 34 ATPs in cell respiration. textbooks use 30 instead of 34. And the reason is your book is not counting these two. It begins here with the preparatory. Really in cell respiration, if you're not including glycolysis, you're not including these right here. So, all right, that's the way they want it. I can explain it that way. We're going to start with those, but I'd like to explain to me, you have to do glycolysis before you do cell respiration. You know, everything from this red line down is cellular respiration, but you have to do glycolysis, so why not throw that in? Include that in your total of numbers of ATP that you're going to produce. Just throw it all in together, lump it. To do it, so why not lump it? I'm a lumper, not a splitter. Those are real terms in biology. People who are lumpers and splitters. I'm a pretty good lumper. Anyway, some people like to split things down into split hairs. You know, I'm like, what? You just need to understand the idea of how this thing works. I'm not a splitter at all. Okay, so what we're going to do, we're going to take our hydrogens, and we've gathered those, and we put those on carriers, NADs or FADs, and we've already made a little bit of ATP already, 2 net in glycolysis, 2 in the Krebs cycle, 2 ATPs directly, and then we put a bunch of hydrogens on carriers. So all of those hydrogens we put on carriers, we're going to run through this ETS. So this is the ETS system where we have all of the proteins embedded in our cristae, the inner membrane of our mitochondria in our inner envelope, depending on how you would say that. And again, it's a lot more complicated than this. So we're going to put our carriers in here. So we're going to take our NAD H2s, or we'll take our FAD H2s. We do both. FAD H2. And we're just going to move those from one carrier to another carrier. We'll pass them, and then from one to another carrier. And we're just moving the hydrogens. And then we're moving them to another carrier, and then we're moving them to another carrier, and then we're moving them to another carrier. And every time we're doing this, we're moving the hydrogens. Now, at some point, and it isn't necessarily the last protein, but again, I'm a lumper, not a splitter. I'm not one who goes, ooh, you need to know exactly where the hydrogen is split into the proton and the electron, and it happens. At which point, I don't feel it's necessary at a freshman level, personally. But, so the hydrogens are eventually split. So protons are going to go out here. We have 2 hydrogens, so we'll move 2 protons out here. And then the 2 electrons are going to go in here. But they won't go to the inside of the inner membrane, the 2 electrons, unless we have one more thing. And this other thing that we need is very important, critical, and that's why I'm using green, because it's oxygen, O2. Now, I know you've never heard this before because it's never come out of my mouth, but oxygen is electronegative, meaning that it tends to pull electrons. So, this is why you breathe. Most people in the world can never really tell you why you breathe oxygen. They just can't do it. You go, why do you breathe oxygen? They go, well, I got to have it. I'll die if I don't get my oxygen. You go, well, okay, but why would you die if you didn't get your oxygen? They don't understand. Where does it go? I'll ask my nephew, where does the oxygen go that you breathe? And he'll go, well, okay, it goes into my lungs, and hopefully at this point in his life he knows exactly where it goes. I need to quiz him on that. He's 21, and he did finish a diploma. So he has the big quiz coming. About time he got it. But anyway, so, and when he was younger, you go, okay, it goes into my lungs, and then where's it go from there? Well, it goes into my, from there, well, then it goes into my cells. Where does it go from there? I don't know. The cells need it. Obviously. That's it. That's as far as he could go. He didn't know. Okay. This is the rest of the story. This is why you need your oxygen right here. Why you breathe. Would that be significant to anyone? Well, I think it should be very significant to everyone. Wouldn't everyone want to know why they breathe? Really? What's the real reason? Why are we taking in oxygen? Tell me, what is the real reason? It's easy. I can tell you. Oxygen is electronegative. It tends to pull electrons off of things. We're going to pull the electrons off of hydrogen. So it grabs a I knew this was coming. All right, so we're going to make our oxygen negative. This is why we just breathe. This is the point. This is when you're going to take another breath here, and there you did it. You did it. You took another breath. It was so that oxygen can go in here, so that it would pull the electrons off of those hydrogens that we have collected, and then we'll put the proton between the outer membrane and the inner membrane. That's where our protons ended up, and the oxygens are all going to pick up. And so you keep breathing oxygen, and they keep going to the inner membrane. And they keep pulling the electrons off the hydrogens. They do it over and over and over. And so as they do that, then we keep putting our protons out here. So this process where we're putting hydrogens on NAD, or we're putting hydrogens on FAD, we do this over and over and over. It's called glycolysis and cell respiration. It doesn't end. You just continues to run. You keep throwing hydrogens on carriers. You keep doing this. Okay. So at some point, though, so our oxygen is in here. The whole process would shut down if you didn't have the oxygen in there, because nothing would pull the electrons off of the hydrogen. Therefore, the hydrogen wouldn't split apart. And what we're going to do with those, and you know the end of the story already, but what we're going to do with these negative oxygens and these positive protons over here, we're going to get them back together. So you're going to pull the positive proton in, and you're going to pull this oxygen that's negative in. Now, if I get a proton and an electron together, like right here, what have I created? One proton and one electron. What is it called? Hydrogen. I'm rebuilding my hydrogen. I pull it apart. Proton goes over here. Electron goes over here. And then I get it back together. You're going, well, that's pretty stupid. Pull it apart. Push it together. Or they automatically attract. But I'm doing it with such massive numbers of positives and negatives that when they slam together, not only do I get my hydrogens, so if I put hydrogens on oxygen, what do you think we're going to create? What's a product? Hydrogen going to oxygen. What could it possibly be? That would be harmless. Water. That's what we make. This is not rocket science. We're not building rocket ship. That happens in second semester. Not really. But we're going to put the positive the positive proton back with the negative electron. You're making hydrogen. We pulled them apart, the negative and the negative electron, the positive proton. We pulled them apart. Now we're going to put them back together. So if I put my electron and my proton together, I've rebuilt my hydrogen. If I put my positive proton and my negative electron together, what's one thing that's coming out of all of this is water. Totally harmless. Metabolic water. It's not anything you'd actually consume, like the coffee has some water in it. It is a diuretic, however, so the more coffee I drink, the more urine I produce. So I actually lose water by drinking coffee. You can dehydrate when you dehydrate by drinking coffee. So that's why I'm very thin, shriveled up, and have all these wrinkles. I drink a lot of coffee. And it gives me a little buzz, which I happen to like. Okay, the legal buzz. So I've made water. I got my oxygen that had an electron on it, and so I pulled my proton with it, and the proton and the electron got back together to make hydrogen, and it went to the oxygen. So I'm going to make water. That's one product of cell respiration. The other thing I do is I make a lot of energy, because if I if I combine my positive charges with my negative charges, you know, that's like putting a north pole and the south pole of a magnet, getting them close together and then turn loose of them. They automatically pull together. And when they hit, there's energy released. Sure. And a big enough magnet that would, big enough positive charge over here and a big enough negative charge over here, if it's big enough, I could crush an automobile flat. Yeah, big enough positive, big enough negative. They pull together. It just like flattened out a Lamborghini till it was like, you know, an eighth of an inch thick. Be real long. Yeah, but we wouldn't want to crush a Lamborghini. Some of us would cry. Me. Anyway, so positive and negative, getting those back together, I've created energy. Well, when you create the energy, what we're going to do is we want to use the energy to do something. So what I'm going to do with it is I'm going to take ADP plus a phosphate, just a PI, PO4. PI is PO4. I'm going to put a phosphate on adenosine diphosphate, and so what comes out of this is ATP. So I produce my two products. So my two products of this whole event for cell respiration would be I make some water plus I make some ATP. Those are your two products. Now, having done all of that, then let's go back and count up how many ATPs we're actually going to produce. Because keep in mind, I did say right up here at the top, I said that for every NAD that's going into the electron transport, we're going to make 3 ATPs if it's carried in there by NADH2, and we're going to make 2 ATPs if it's carried into the electron transport by FAD. So, knowing that information, we can do a grand total how many ATPs are really produced. And these processes do have some names, but this whole system right here, this is an electron transport system, ETS, or some people call it electron transport chain. I think they're using electron transport chain more often than they're using electron transport system. It's just terms. Yeah, and all that happens right here. You're just taking all of the hydrogens that we've collected, and we're running them through these protein carriers, and at the end we pulled apart. Protons go out here between the outer and inner membrane. The electrons, of course, are pulled to the oxygen. This is why you breathe, in order to pull hydrogen apart. Why you breathe. And then at some point, the electron, which is on the oxygen now, and the proton slam together, and that makes water, which is harmless, but it also generates enough energy to make ATP. That's the whole process. And I said we're all hydrogen powered. Anything that's living is hydrogen powered. Now not all cells on the planet get to do this whole process, because bacteria, they don't even have mitochondria. They're small, little bitty, tiny. You know, they do ethanol fermentation for the most part. They can do some other things, but at this point, ethanol fermentation, that's good enough for us. For the bacteria. bacteria. And then, of course, if it's a eukaryotic cell, they would have a mitochondria, and so they would be doing cellular respiration that do all of this. You know, and you look at the whole thing and you go, man, that's a whole bunch of stuff. It is, you know. And if you're one to go, man, that's just nothing, you know, I don't like this, just too much. You know, I always say, complain to God. I didn't do it. I didn't have anything to do with it. I didn't build this system. I think it's an absolutely beautiful system because we're making energy by using the simplest element on planet Earth. And we have built, or God has built, a system that is the most energy efficient system on the planet. Nothing else can be anywhere close to this energy efficient. The efficiency is amazing. It's incredible. Hydrogen-powered automobiles, you know, I'm just like, why don't we have those? Because this system is so simple. Get your positive and negative back together, pull them apart, and then slam them together. You get energy. What could be easier? I mean, really? You know, and it's been going on for how many years? 3.5 billion. And we're going, how are we going to run this automobile thing that we want to all ride in and have and blah, blah. Oh, I don't know. Let's just drill for oil and gas. Yeah. Let's destroy the environment. Yeah. You know, I'm like, you know, God gave us the best system in the world. Right here, it's called the cell. Look in there. It's going to tell you how to run something. Use that system to run something. Now you're talking. Now you're talking. Now you're working with the natural world and you're doing something that I think God wants you to do. Personally, this is the way I look at it. And, you know, if you're totally atheist and don't buy into any of that, then that's cool too. There's a place in the world for everybody. Okay, so what I want to do is I do want to add up, and just quickly, I want to add up all of the ATPs that we're manufacturing. So let's just do that. I'm going to leave that 3 ATPs for each of the NADH2s, and then I'm also going to very cool. That's so much faster than an eraser on the chalkboard. Very cool. All right. So when these two in glycolysis go into the ETS, electron transport, for each one of those, we will make six ATPs right there. All right. We made 2 right here. We didn't go into electron transport, but we did make 2 ATPs. And then these go into electron transport from the preparatory reaction. And for each one of them, we make 3 ATPs. So that would, again, be a total of 6 ATPs. Okay. And then Krebs cycle, we've got 6 NADH2s, which is really 3 for each pyruvate. So that's a total of 6. 6 times 3, that going into electron transport, you get a total of 6 times 3, which is 18 ATPs. All right. The ADs, each one of those makes 2 ATPs. So the 2 times 2, because you only get 2 ATPs. Once you take the FAD into electron transport, so 2 times 2 gives you 4 total ATPs. And we did make 1 ATP in the Krebs cycle, citric acid cycle, 1 ATP for each pyruvate. So, you know, these don't go into electron transport, but we did make a total of 2 ATPs here. So let's just add all this up. All right, so let's go. Let's see, 6 and 6 is 12, that's 14. This is the way I like to add. because I'm a moron. Okay, 22 ATPs. Those two, these are just 2 ATPs. So then I add those up. It's a lot easier to add that way. So I have a total of 14 and 22, that's a total of 36. And these two, that's a total of 38 ATPs. All right. Most books will tell you 36. They say anywhere between 36 ATPs to 38 ATPs. Well, I've already said that we would eventually have to subtract 2 ATPs because these NADs that are out here in the cytosol, it takes some energy to get those into the mitochondrion. So I have to subtract 2. So that's where I subtract my 2 ATPs. And then what I'm really left with, of course, is just the 36. So I use 36. If your book says 34, it's because they're not even considering the 2 net ATPs that you made in glycolysis if they say 34. And so that confuses people. It's like, say that again? Well, it's on tape. So you can listen to that as many times as you'd like. But yeah, they don't consider those part of the cell respirations, the one that you made in glycolysis. Okay. Anyway, there are a couple of terms that I do want to give you, but they're just a couple of terms. What they call these processes, substrate level phosphorylation is one of them. The other one is chemiosmotic coupling, and we've already done it. You've already seen it. I just didn't throw names at it at the time, and I will just briefly mention that tomorrow. Okay, we're done, and you have yourself the best day of your life because you never know. It may be the last one.